This is an explanation of the solution PDF to the buoyancy lab, which was supposed to be an experience with investigating Archimedes' principle and the idea of buoyancy. So in the first part, you're supposed to draw some free body diagrams where the free body diagram is for your body, and you're, in the first one, sitting on the edge of the pool with just your feet dangling in. In the second one, you're halfway submerged. In other words, the water reaches up to your waist, and then you fully submerge yourself in the third one. And we're supposed to draw the three forces on you in each case. And I suppose part of the challenge is to figure out what the three forces are on your body. Your weight is certainly, the earth is pulling down on you, so your weight force should be the same in all three, right? The earth doesn't change depending on how submerged you are. And the other two forces are, well, of course, there's a force upward from the ground, either, when you're sitting up from the ground where you're sitting, or if you're standing up from your feet, right? So that's what F ground is. And the third one is that upward force from the fluid, and that's what we call the buoyant force. And so when you just have a little bit of you in there, you'll feel just about your same weight. You don't really notice it when your feet are just dangling in the water. And that means the force up from the ground almost equals and balances out your weight force, but it's a little bit less because there's a little bit of additional upward force from the fluid. When you're half submerged, maybe there's less of a force up from the ground because more of the force is pushing up from the fluid. And then when you're totally submerged, the details kind of depend from person to person and how well you float or sink when you're submerged. But in this case, I'm imagining that you still sink a little bit, so maybe you don't have so much air in your lungs. So there's a tiny force up from the ground, right? But when you're completely underwater, it hardly takes any force from the ground to hold you up. There's a much bigger force from the fluid, and the sum of those two add to the weight force. And in all three of these cases, the sum of the three forces should be zero because you're not accelerating at all. Okay, in this first experimental part where, in lab, of course, we actually did this, we had a metal rod on here, and the idea is you would measure the radius of this cylinder and the length of the cylinder. Here in this version, I just gave you some made up numbers. So here we've got a metal rod, here's its radius in meters, here its length in meters, and we imagine we weigh it on the digital scale. Here's its mass in kilograms. We're asked to calculate the volume of it. That's just pi r squared times the length of it. So I did that in cubic meters. And then the density in kilograms per cubic meter is just the mass divided by the volume. We've got the mass and we got the volume. So here, in case you haven't noticed, I'm putting my answers in red. Down here, when the rod is lowered into the water, how will you use the force sensor reading to determine the upward buoyant force from the fluid? So we're going to be determining what the buoyant force from the fluid is. It's hard to measure that directly, so we're going to measure it indirectly by hanging this rod from a force sensor, right? So if the rod's not submerged, as I have it shown here, the force sensor should just read the weight of the object because those two forces balance each other out, right? The string tension going up, which is what the force sensor reads, equals the weight of it going down because this thing is not accelerating. When it's partially submerged, we also have, just like in these cases, an additional fluid force. Like we would have the tension, the fluid force, and the weight force. And the sum of those three add to zero. So that's what I'm saying here. If we do the sum of the force y components where plus y is up, is zero, that means the fluid force and the scale force come in with plus signs, and the weight force comes in with a minus sign in terms of those y components, and they add to zero, and therefore we can solve for the fluid force, which is the weight force minus the scale force. So we read that from the scale's reading, and we have already calculated the weight for it. I guess we could calculate it. We've got the mass from the scale. We just multiply by a little g to get the weight force, right? Turn it into a force. So that's how we're going to calculate what the fluid force is, or the buoyant force. So we're supposed to now fill in some data points in this table right here. So the idea is we're going to submerge the rod by a certain fraction, right? So first 0% submerged, then 25%, then 50%, then 75%, and then 100% submerged. And in the first case, where it's not submerged at all, we're supposed to figure out what the force sensor reading is. Well, we can do that just by saying there is no fluid force, so the force sensor reading must balance out the weight force. So this is just the mass times little g. That's how I figured that in. And there's no fluid forces there. There's no volume that's submerged, so all of those are 0 in that case. Then we're imagining in the other cases, when I submerge it a quarter of the way, halfway, 3/4 of the way, we're going to read the force sensor reading and then use our formula up here. The fluid force is the weight force minus the scale force, to determine what the upward force from the fluid is. So I've just used that. I calculated the weight force by multiplying the mass times little g from above and subtracted off the scale force to the left, and that gives me the upward force from the fluid here in all 4 cases where it's partially submerged. And then we're told that we're supposed to calculate this column and this column by only using the geometry of the cylinder. So the idea is, what is the volume of the rod which is submerged? Well, if it's only a quarter submerged, it's just 1/4 of the total volume of the rod, a half of the total volume of the rod, and so on. And this is the total volume of the rod. And then to get the weight of the fluid displaced, which obviously has to do with Archimedes' principle, we take the volume of the rod that is submerged, multiply by the density of water, that's 1,000 in SI units. That would give me the mass of the fluid displaced. But if I want the weight of it, I've got to multiply also by little g. So this is the volume, this is this volume times 1,000 times little g. That's what these numbers are. That fills in the table. We're doing the same experiment here, but with a different density substance. This is with a wooden rod or wooden cylinder. And again, we're given its radius, length, and mass that presumably we've measured in the lab normally. And then we're going to calculate its volume and density. And so that we did the same way as before, pi r squared times L. And the density is just the mass that we measured divided by this volume that we just calculated. Filling in the same things in the table down here in the same way. The only thing that's a little bit confusing or different is that, you know, of course, when the object is not submerged, this piece of wood is not submerged, the force sensor is pulling up on it, and that's a positive reading for the force sensor. So when it's not submerged, positive reading. Quarter of the way submerged, positive reading. Then halfway submerged, it's very close to 0, and that means it almost floats by itself halfway submerged, and so the force sensor hardly has to exert a force on it at all, but it's slightly negative, and that means it's pushing down slightly on it. And then to submerge it 3/4 of the way, we actually have to push down significantly with the force sensor. So when it's pulling up, that's a positive reading. When it's pushing down, it's a negative reading. And even more, to submerge it all the way, we have to push even harder to hold it under. It doesn't want to be submerged. So calculating all the numbers the same way and filling in the table, that's not too bad. Now, let's see. The next question is, in both of these cases, do they agree with Archimedes' principle, which is the fluid force, or the buoyant force, is equal to the weight of the fluid displaced? We can check that directly in the table here because we calculated the upward force from the fluid just from the force sensor data. And then here, we're calculating the weight of the displaced fluid just from the geometry, and they do agree. These two columns are exactly the same there. So that verifies Archimedes' principle. Same in this case. The numbers are slightly different because of some rounding I did, but that's pretty close agreement between those two columns. So that's Archimedes' principle. The fluid force or buoyant force is equal to the weight of the fluid, which is pushed out of the way by virtue of pushing a certain fraction of it under the water. In this case, we're thinking about the derivation, which was given in the slides, derivation of Archimedes' principle in terms of a cylinder, and in that case, the forces going around the circular outside, the pressure forces would be pointing radially inward, but they're going to cancel as you go all the way around, and therefore I'm not drawing them in this diagram. We're only drawing the vertical forces. So there's pressure, and that pressure is pushing up on the bottom. That's why F bottom, the pressure on the bottom is pushing up. That's why it's shown going up here. The pressure on the top is pushing down. That's why it's showing going down. And of course, the weight force is going down. So here in this case, we're imagining we have a cylinder that we're going to put under the water, but we're imagining the same exact geometry, but just of water inside water. So this cylinder is made of water, sitting in water. Of course, it's neutrally buoyant. It doesn't want to go up or go down. So the sum of these three forces has to be zero, because this thing doesn't want to rise or fall. It's just water in water. And that means the sum of these three vectors should add to the zero length vector. That's being stated up here. And the difference between these three cases, this is a case where we're imagining that same cylindrical shape but filled with water. Here is a cylinder which is more dense than the fluid, and of course the bottom and top pressure forces don't change. It's the weight force that changes. So if the object is more dense than the fluid, the gravitational force gets longer, and that means these no longer add to zero. They add to a net force going down, and this object's going to sink. That's what happens when it's more dense than the fluid. When it's less dense than the fluid, the weight force gets smaller, and that means the sum of these three forces are going to add to a force that's going upward, and this object is going to rise to the surface. Finally, there's something about an object floating. So here's a spherical object that's partially submerged, and we're supposed to say, we're going to call the total volume of the sphere V object, and we're going to call just the fraction, or the amount of volume that is submerged under the fluid V sub in this case. And we're going to call the density of the object rho object, and the density of the fluid rho fluid. And the idea is, by using the fact that this thing is just happily sitting there, so it's not accelerating in the vertical direction, the vertical force components have to add to zero. By using that fact, let's solve for what the ratio of the submerged volume to the total object volume is. And we can do that by writing the sum of the force y components is the buoyant force minus the gravitational force, right? In this case, there's no other forces. There aren't any strings pulling up on it. So fluid's pushing up on it, gravity's pulling down on it, and those two forces add to zero. So let's flesh those out a little bit more. The buoyant force is supposed to be the weight of the fluid displaced. That's equal to the volume that is submerged times the density of fluid. The density of the fluid times the volume that's submerged would be the mass of the fluid that's displaced, times little g gives us the weight of the fluid that's displaced. So this is the weight of the fluid that's displaced, and then the gravitational weight of the entire object is just the volume of the whole object times its density. That's the mass of the whole object times little g gives me the weight of the whole object. Okay, so the sum of those two are zero, and we can then solve for V sub over V object. The g's cancel out, and that tells us the submerged volume to the total volume is the object density divided by the density of the fluid. So, for example, that tells us if the object is 2/3 the density of the fluid that it's sitting in, right? If it's a lower density than the fluid that it's sitting in, it's going to float like this, right? Let's suppose it's only 2/3 of the fluid density. What that means is the ratio of the submerged volume to the total object volume, or the fraction of the volume that is submerged, is 2/3. So if it's 2/3 of the density of water, 2/3 of the object is submerged. If it's 1/3 the density of water, it would be 1/3 submerged, right? If it's 9/10, would be 9/10 submerged. So that's kind of a good rule of thumb, so you can sort of eyeball exactly or loosely how far it gets submerged. And that's it for this little artificial lab experience.